So let's start a third lecture on NLP with deep learning. And today we're going to be talking about, so remember we had this task in NLP split into text classification and text generation, while the classification was for some reason easier because of the evaluation is easier as we had on the exercise, like precision, accuracy, and stuff like that versus blue scores and rouge, excuse me. So we're going to start by building models for text classification. So that's our today's goal. Also, I had some feedback. Well, so thanks for the feedback, the anonymous feedback. It's really helpful to get something, just to understand how to improve this thing. So some people complain it was super slow. Some complain it was okay speed. So I think it really depends on your background knowledge, like how you know how much you already know. So then it feels maybe slow, like the math is easy because you had optimization before or you had machine learning before. If you're new to that, you might be just saying, well, okay, this is too much. So we had comments, and I'm afraid I don't have a best solution to that. So if it's slow for you, you can do other stuff, right? I mean, do what you want. It's your freedom of choice, okay? But apart from that, I think we clarified everything. Okay. So thanks for that. I'll open like another round of feedback, let's say in 2-3 weeks, like anonymous, because I believe it's a nice way to really improve the course. So motivation for today. Okay, what are we going to achieve? So we are gonna tackle a example task, and this example task is going to be very simple. It's gonna be binary sentiment classification. So if you remember sentiment classification, we have this IMDb dataset which was the movies, and they were simplified for this reason. Were simplified into binary tasks. So it means a movie is either a piece of text, which is a movie review, is either positive or negative. So this is the IMDb dataset from lecture 1. So you can look it up again, some citations and some details about it. So we will learn today, or when you come out of this lecture, you should be able to understand a simple but still powerful supervised machine learning model. So even if you don't know anything about machine learning yet, you will know today. And you can be proud of yourself. Okay, I know machine learning. I can build supervised machine learning and classify reviews. Even you can build. Maybe we'll build it next week, like just really from scratch. So we're gonna learn this model, which is known also as it has different names. So one is a logistic regression. It's known also as a maximum entropy model, and maybe a simple neural network, but it's not really it's not deep. So it has many names. Yeah, a single layer neural network. And it is an essential and important building block of deep networks. So we will see this kind of simple classifier, simple model will be super helpful building block for stitching it together and having it in multiple copies and building something which is much bigger model. Okay, so this is what we are going to achieve today. So, okay, so we have to talk about supervised machine learning on text data. What does it mean? And we're going to be using again some math notation, but it shouldn't be surprising. So we will use we had already calculus a little bit in last lecture. So function minimization and stuff like that. Today there will be a very little bit of linear algebra. But if you know what a vector is, and a matrix, you're good. I guess this is what you really need to do deep learning. You don't need more. If you know more, you understand more of more subtleties, let's put it like that. So what we have here is scalars. So what is a scalar? It's just a real number, mostly. So we're gonna use lowercase letters. So just simple X, Y, B, so that they're gonna represent scalars. Okay, so they're gonna be mostly real numbers. Then we're gonna present vectors. So if you have physics, maybe, so in physics you have these vectors with this arrow. Right, this is what I had it in high school at least. So these are vector in physics. We're gonna use vector as bold lowercase letters. So W is a vector, and it could be, for instance, in n dimensions. Okay, well, we had vector before. I mean, vectors were, for instance, the gradient is a vector, for instance. Okay, so we have vectors and matrices. Okay, so matrices are lowercase, so matrices are 2-dimensional arrays basically in a from a computer science perspective, and also it's something very different from the linear algebra perspective. It's a linear map and has some properties and blah blah basis and stuff like that. But we don't go there. We don't need it. It's just a matrix. I mean, it's just some rows and columns of numbers. All good? It shouldn't be surprising. Okay, nice. So, where of course we want to access elements of these vectors or matrices, so we are going to be using this parenthesis as a index operator. So nothing surprising again if you know Python and you have a, let's say, vector. This is vector, and you can access the eth element. I mean, this is a standard indexing thing from in Python as well. So we're going to use that. So B, original is like this lower index here for the eth element of vector B. Okay, so this is what we're going to use. And then, of course, matrices have rows and columns. And I guess this is a standard notation. The first index is the row, and the second one is a column. Everybody agrees on that. Do you remember that as well? Like from linear algebra, like you have first rows and then you have columns. Okay, why it might be confusing? Because of different implementations of, well, not really. I mean, if you have just a matrix and you use, for instance, NumPy, you're going to be indexing it in the same way. But when you go to multidimensional arrays, like you have a list of matrices, which is a three-dimensional array, then the indexing gets a little bit tricky. So you have to really pay attention. I mean, you never flip these dimensions, but just pay attention to the indexing. It could be tricky in the implementation. Like on the paper, it looks very nice. So we're indexing the matrix and obviously, you know, eth row and j column. Okay. So this is just a setting up a background here. Also, we're gonna use a sequence of vectors. So we have, let's say, n vectors. So, and we wanna have a sequence of them, a list of vectors. So we're gonna use this 1 to n notation. It's also same in actually in NumPy. So you're using, or in Python, you're using this column for slicing arrays and stuff like that. So this similar notation here. And also one operation, which is not so common, but we might be using it, is a vector concatenation. So what is vector concatenation? Okay. Well, let's start here. Okay. How we understand vectors. So in mathematics, a vector is mostly this thing. 1, 2, 4, 9, whatever. So in mathematics, you have a column vectors, right? This is like what the linear algebra people are saying vector is. It's a column. Well, from a computer science perspective, it's much better to have it, as a list of numbers and treat it like that. So we're gonna use row vectors. Some people might use in deep learning column vectors. That's fine. So you always have to know or kind of infer from the context what are they using. We'll be using row vectors very explicitly, and it makes multiplication of matrix of vector and matrix maybe a little bit different from what you know, but we'll come to that. Okay, but we're using a row vector. It's just a bunch of numbers. So for us, mostly a vector is just a bunch of numbers, and it's a list or it's a row. So which means if we have vector concatenation, so we're not gonna use that. We're gonna use this 1, 2, 3, 4, so on. If we concatenate two vectors, so we had vector x, and want to concatenate with vector, let's say y, which is 6, 7, we end up with a vector 1, 2, 3, 4, 5, 6, 7. So we just stitch them together. Okay. All right. Cool. So yeah, it's simply a list of 1D or 1D array of numbers. That's it. That's our vector. All right. Let's move on. So now, okay, obviously, I mean, we have multiplication, so we need to, everybody should know that, I guess, but it never hurts to kind of, recall again how the multiplication of a vector and a matrix and maybe addition of two vectors, how it looks like. So let's say we have a vector in, so this d in is just a number, so it's number of input dimension. So the input dimensionality of our, so okay, we have a function here where it outputs a vector, and the input is a vector and another vector and a matrix. Okay, so we're gonna multiply these two things together. add up the B vector, so the result should be a vector. How exactly it looks like for here, an example for where the vector here has dimension of 3. Okay, so this is 3, which is the dimension of input. Well, so as you see, while multiplying a vector by matrix, because we're using row vectors, if you remember from linear algebra, you would basically say first a matrix times a vector to get the same result, because the vector are column vectors, right? But here we're saying, okay, we're multiplying a row vector by a matrix. So the multiplication of a matrix by a vector, the ordering matters because you have to match up the dimensions. So that's why I'm saying we're using row vectors, and maybe this looks different than you would expect. Maybe you would say, oh, I want to multiply W times X, and maybe you, yeah, if X were a column vector, you would write it like that. But it's like what you know in linear algebra. But we're doing the other way, so we're multiplying just X by W to get the same result, another vector. So we have an input vector, and then how the multiplication works. Okay, so how do you multiply a vector by a matrix? How do you do that? Do you remember that? From this times this, okay? Plus. Okay. Okay. X1 times that one, X2 times, okay, so you basically take this, project sort of, or put it on this column and multiply each element together and sum up. Okay, everybody knows how to multiply a vector by a matrix, or matrix. Well, we're not going to multiply matrix by matrix, maybe later on. Okay, this is interesting, this is cool. So we're basically having these three-dimensional vector multiplied by this matrix. We're going to end up with what's going to be the dimension of the output. 2 dimensions, exactly. So the out is going to be 2. Okay, so this is interesting. What is it? What we are doing? We have a vector of 3 dimensions, and we multiply by a matrix and end up with fewer dimensions. Okay, it's interesting. Nice exercise, but what does it mean? What is it in life, in reality? You have a vector of 3 dimensions and you multiply it by matrix and you end up in 2 dimensions. Oh, you're doing something with the vector and the matrix. Yes.
Well, if I look at the matrix just as a function that operates as a vector,
okay. You can
increase the dimensionality in the vector. If I just
yeah.
have a vector in a room, and I sort of project the vector.
Exactly. That's the point. So a matrix is a function. It's a linear map, by the way, formally. And you are projecting the vector from some 3 dimensions, in this case, into 2 dimensions. Okay, this is interesting. So you're taking a vector, which is in here somewhere, like this here could be a vector, and you're projecting it maybe, you know, on the floor or on the wall. Interesting. So it's basically a projection. What does it mean? It has a special properties. I mean, this projection has special properties, and there's some special property about a matrix. So if you have 2 points and you project them somewhere else, something will be kept the same or similar. You preserve something. So you have 2 points somewhere, and you project them with a matrix to somewhere else, maybe on a wall. Okay, so I have an object, here 2 points, or maybe a triangle, and I'm projecting that on the wall using a matrix. There will be some properties of the triangle kept. And this is very important. Any idea what these properties could be? Think about it like visually. You take an object like my phone, and you basically close one eye. So you have, it's 3D object, so a couple of vectors maybe. You close your eye and you look at a wall. Okay, so it's 2D now. If you look at it with an eye, it's 2D, and it keeps some properties. Like there are some properties of this object still be present in 2D. What is it going to be? So maybe think about it. What is it not? So the object doesn't make any curve. It doesn't twist. It's not bending, right? It's not bending. It's just, yeah, okay, a line is a line, right? I mean, the edge of the phone is still the edge in the 2 dimensions. So what does it mean? Well, it's a linear projection. So a line remains a line, and everything is basically scaled in a ratio, so to say, right? I mean, you're scaling a thing somehow in a way how you look at it. But, you know, triangle inequality will be triangle inequality. You're not squeezing the space somehow. You're just projecting it. You know what I mean? You're not bending the thing. I mean, it's still something which, if there is a line, there will be a line in the new dimension. This is important. So lines are preserved. That's why it's called linear map. So it's linear, which means line. So line will be a line, and there will be some things around it, right? So you're not doing anything with the space. You're just projecting lines into another lines, sort of in different dimensions. Does it make sense? This is a key property of a linear map, because it's very helpful for, you know, maybe reducing the dimensionality of the vector, but some properties of this object will be still there. You know, you cannot add more information. Oh, sorry, I don't want to talk about this. You're basically propertying the linear relationships between the points. So x plus y is equal to some fx plus fy and stuff like that. So there are some properties of this map. Okay. So interesting. So we projected that onto some other space, and the way we project it is the matrix here. So we use a matrix, whatever is in there. Depending on the content, you would project in something else, but it's still a linear. It's a linear projection. Okay, and then we have this plus the other vector. And obviously, I mean, since this output has dimensionality of 2, and this is 2, then you end up with a 2-size vector. So we're projecting things, and then what we're doing here, this is some sort of offset. So we project it, and then maybe move a little bit in the space, you know, in the 2D, and we move it somewhere. This is the B vector, right? So we first somehow maybe rotate it or do the projection, but then move it somewhere else. But, you know, all the properties, the linear properties will be kept after this operation. That's why it's called a linear operation. It's a linear function. It's a linear function, but we're working in multidimensional space. I mean, we had a previously like linear function as these are not vectors, these are real numbers. Ax plus b, it's a linear function. You take a point and project it using the line to some other space, right? So we project these 2 points, and they will end up maybe here and here, but the ratio is preserved. Maybe they're shifted a little bit, but the ratio is preserved. Okay, so all right. So it's easy, but at the same time, it's somehow a very interesting thought. Like we're projecting things from one space to another space. It will turn up to be essential for any sort of learning. Okay. Good. Any questions? Excuse me. All right, let's move on. So now, so we have this multiplication, and if we have a matrix which has just basically one column, we can simplify this this vector times matrix multiplication by dot product. So what is a dot product? Dot product is defined. So I mean, this is definition of the dot product. So you take each element of, so you have 2 vectors, they have to match in the length. So here, for example, we have 2 vectors, x and w, and they have the same dimensionality. So x is this is wrong. En, yeah, this is wrong. This should be also the n, I guess. because they have to match. So their length have to match. We have 3 dimensions here, 3 dimensions here. Sorry, yeah, 3 dimensions basically, exactly. Is it 3 dimensions? Yeah. And we take this one plus this one, sorry, this one multiplied by this one, this multiplied by this, and this, and this, and sum it together. This is the same operation as we did with the multiplication of a vector and a matrix. So it might be a simplification if we have just a vector of real numbers, not a matrix. Okay, so this is a way of writing this operation as a dot product if these vectors, if W is a vector, not a matrix. It's just much simpler, and we will show later that's kind of useful to think about it like that. Okay, so dot product. We will talk actually about the product more into detail because it has some special properties, but for now it's just a multiplication of 2 vectors element-wise and sum them up. Okay. Any questions to dot product? Everybody's with me? Okay, cool. Yeah. Let me fast forward because I forget what I'm trying to say with this. Okay, supervised classification setup. So we want to project our input into some output. And for the classification, okay, so what is a classification? If we have a binary problem, we might have a some sort of input which will be a numerical, it'll be vector. So we'll talk about it, how to make a text into vector, because this is the crucial question. But let's say in general setup in supervised machine learning, your input is a vector. Okay, you have a vector, some point somewhere, and you want to say, oh, is it a positive review or negative review? Is this dot positive or negative? So each of them will be labeled, and it's up to you to decide, but mostly 0 and 1. So it's a function basically. If you want to classify a point and say, well, I have this new review which is expressed as a vector, you want to say, well, is it 0 or 1? Which means you want to build a function that takes a vector of higher dimensions and outputs a scalar. Okay, so you want to output 0 or 1. Does it make sense? So if I have let's say just 2D space, and here this is going to be x1, this is the x2, right? So I have x vector, which is the input to my function, which has just two dimensions. So x1 and x2, right? So this is a vector of two items. So, and basically it's a dot somewhere. So, and I want to kind of understand, is this dot 0 or 1? Is it positive review or a negative review? So we want to build a function that for any input here, any particular review, which is now represented very simplistically as two, so to say, features. Okay, so it's a feature by two features, so the size of the input vector, and to decide whether it's a 0 or a 1. Okay, so this is a function. Basically, we want to build a function from Rn to 0, 1. This is our classifier. Does it make sense? Okay, so the big question is here, what the heck is here in this? How do we get from text to a vector of real numbers? And we're going to tackle that. But once we have this, we just want to build a function that maps everything to 1 and 0, or maps any input to 1 or 0. And this function could be any function, right? I mean, you could build, what could be the easiest function you can ever write? Like, it doesn't have to be a mathematical function. It could be just, you start coding and say, if there's a word good, then it's 1. Else, if there's a word bad, the result is 0. Else, if there's a word, and so on. You can code it up. I mean, we talk about it in lecture 1, but you don't want to do that because the sheer amount of text is infinite. So you want to build something much smarter than just a if-else kind of program, okay? So it will be a mathematical function, which gives us some better properties for maybe learning. And we are saying that, okay, by using a linear function or a linear map, we are putting sort of, well, we have a set of hypotheses, so hypothesis class. So this is a set of all functions which can basically serve our purpose. And we are saying, yeah, maybe we want to have just some subset of these function, and the solution will be maybe, so this function might be just a linear function. Will it work for all cases? Well, we will see. Of course not. Yes, you have a question. Say again. Sorry, for what x? Oh, okay. Yeah. Exactly. Will it work for? Let me put it down, and I believe I have a couple of slides about it later, either today or next week about XOR function. But a linear function will not learn this XOR function, yes, and we will show it exactly, I guess, at the beginning of next week. So, but I'm saying, well, I'm going to use a linear function, and it's a simplification, so I'm putting some sort of bias into the solutions which I'm going to learn. If this sounds too abstract right now, this is fine. So you can come to that later to understand it more, and once we get one procedure or one of the models to understand what do we mean by that. So we have the high-dimensional linear functions where we have the input of the in dimensions and the output is the out. So this is our linear function is basically what we had before. So input multiplied by a matrix plus some sort of bias. We call it bias, the B term. Okay, so the X has some input dimensionality, obviously. The dimensionality of the matrix, the mapping has to match the input and the desired output. So we had this example from 3 dimensions to 2 dimensions, right? So this is what we are kind of designing. And also we have to take into account the size of the output. Okay, so again, the vector S is the input, matrix V and vector B are, and now we have the function, so this is a function which we specify by this, and then saying there are the parameters. So we call these parameters. Okay, so we have a function which takes an input and it's parameterized by W and B. So this is a formal, kind of formal description of the function. The function has an input. Well, everything is input to the function, right? Because we multiply X by W plus B. So everything is an argument of this function. But we're saying these W and B are parameters of this linear function. So these are things that we want to learn. Okay, now we're coming to learning. So if we want to project from one space to another, so from the input features from the text, so the vector of the text into 0 or 1, and we have some examples. So we have a collection of input values, maybe k of them. So we have these vectors. So this is basically a list of vectors. And for each of the vector, we have the output, which in the simple case will be 0 or 1. We want to learn this mapping automatically. We want to learn which parameters of our function, so the W and B, are the sort of best, and we'll talk later what best means, but are sort of best to do the job. We want to learn the best projection from our feature space, so from the size of the input vector into the 0 or 1 label. And we want to learn it from data. So we want to build something that if we have k examples in the training data set, okay, training data set, we had it before. Anyone remembers how many training data set was in the IMDb corpus, roughly? Maybe we didn't talk about it. I think like 25,000 something. Okay, so we have 25,000 reviews and a label. So the review is text. We transfer it into vector, and so we have the vector of the review, and then we have the label. 25,000 of them. So we want to learn a function, and it could be this linear function, such that the content of this matrices of the matrix and the bias will work best on the test data. By accuracy, by F1 score, whatever you want to evaluate, like best. And we want to learn them automatically. Any questions? So it's going to be actually even simpler, because for this binary classification task, the output is going to be equal to 1 because we're projecting to one number, either 0 or 1. So it's going to be much simpler, and we will see later. Okay, but in general, we maybe want to project into maybe another vector. So let's move on. Okay, yeah, that's what I said, binary classification. So it's a simplification of that one. So here we're projecting again from the dimensionality of the input vector, but now it's just a scalar. So we're predicting just 0 or 1 maybe. Okay, so that's repeating what I said before. So again, we have it here. We just say that arbitrarily, this is our decision, that the categories of positive or negative will be 0 and 1. So negative is 0, positive is 1. But remember, this is a decision we made, like as a designers of the experiment. You know, if you can say, well, to me, positive review is going to be 0 and negative will be 1. That's fine. It will work the same way. I mean, that's a question. It should work the same way. It will work the same way, but there's some other trickiness like bias in the data, but whatever. You can design it as you want and make the labels as you wish, and it's an arbitrary decision. And you have just to know it. Like if you have a prediction and it comes like 0 out, you have to know, well, okay, is it now negative or positive? But you know, typically we use 0 for negative and 1 for positive in this sort of setup. There could be another machine learning techniques which map, such as supervector machines, which map it to 1 and -1. Okay, because of the trickiness of the SVM, it's just better. But here we have 0 and 1 for a reason. Anyway, coming back here, so we're simplifying this here, and again, the function is a linear function which is now multiplying the input by, it's not a matrix anymore because we're projecting into one dimension. Okay, so here's an example, right? If we have a x1, x2, x3, and we want to multiply it by a matrix, and we want to get just one dimension, what is going to be the dimensionality of the matrix? You should know now. Think about it a little bit. That's not hard. I'll give you a few seconds. Yeah, it's easy. I know it's easy. It's just a sanity check. Like it's Friday morning at 8, and some people just had a sleepless night, me included. So, anyone who hasn't spoken yet, like anyone in the back, what should be the dimensionality of the W matrix? Yes. 3-1. That's a good answer. Which means it's gonna have 3 rows and 1. Yeah, this is actually the only answer. If you say like it doesn't matter, well, it depends. What do you mean by it doesn't matter? It matters. Like absolutely, because if it had 4, so how do you multiply a vector of 3 items with a matrix 4 times 1? Can you do that? You see, okay, so it has to be 3, right? Yeah, and well, before that we projected with 3 times 2, like from 3 dimensions into wall, like 2, so it was 3 times 2. Now we have 3 times 1, so we projecting just on the line. Now I cannot visualize it. I mean, I can take a phone and trying to project it on a line, but it doesn't make any sense because I would have to like look at this flat screen again from the top and maybe then project it on a line. It's kind of yeah, you can find an analogy, but it doesn't really make sense. You're projecting basically a 3D object onto a line. But again, the properties, the linear properties, will be kept. Like the sizes will scale linearly. Okay. Anyway, so but we're not, we're using here the dot product as we had before, so it's going to be a vector of size, the same size. So W dimensionality has to be same as the input dimensionality. Okay. Any other opinions on this multiplication or the sizes of the vectors? Okay. Did you get the same solution in your head? Awesome. Okay, cool. Yeah, so the input is in the form of a natural language text. Well, we have to turn this into a vector, and it's going to be a big chunk of the deal, and the categories we talked about before. Okay, so any question? We're going to be dealing today with binary classification. So we have some input vector, and we want to project it into positive or negative, so 0 or 1. Okay? Everybody's happy? Everybody awake? More or less, yeah. I mean, it's hard. I can understand that. All right. So let's get started. How do we turn text into a vector? That's going to be tough, right? So remember, in the IMDb, we have reviews. So, and here's the text. One example. One of my favorite movies ever, The Shawshank Redemption, which is, I guess, still #1 on IMDb, like the top-rated movie, or used to be like that, is a modern-day classic as it tells the story of two inmates who become friends and find solace over the years in which this movie takes place, based on the Stephen King novel, and so on, so on, so on. So basically, it's a long text. That's what we have, right? Could be like 500 words long, something like that. You just write a long review of a movie which you liked. Everybody saw Shawshank Redemption, by the way? It's a modern-day classic. Come on, guys. Okay. No, it's actually a nice movie. I mean, the book is kind of cool as well. It's a 7-piece book by Stephen King. So, the thing is, how do we turn this, is what we have, into a vector? How do you turn a text into a vector? So, any ideas? Like something which comes to your mind.
Set context where we only have a limited amount of possible texts, we could just enumerate them and
so you can basically enumerate snippets of text and project them on numbers, right? Not a bad idea. Where's the catch? So if I understood correctly, so you have text 1 and you would map it to say some here, like, no, just much easier. You would say text 1 is just 1 and text 2 is 2 and so on, right? You find a map from a text to a number. Yeah, where's the catch? We had it in lecture 1 or 2. You have any idea? No, sorry, I thought you had.
there are so many different texts.
Exactly. There's just so many. Even so, if you have the text of length 4 words, and you have 10K vocabulary size, you are getting into troubles because you would have to write 10K power 4 possibilities. It won't fly. It's a good try, but we should do somehow better. Okay, any other idea? This is the trickiness of the language, because there's just so many variants of writing things. Okay, any other idea? Yes, you.
Every character has to a number of 0 to 256.
Yes.
And then we just say every vector cell represents one character.
That's great, but how long the character? Okay, so you would say this is just so each character, you would represent each character as a byte. So this would have, let's say, 800 times something bytes. Yeah, why not? It would be like 800 characters. Sorry, not words. So we have like 1,000 characters here. It would be like 1,000 size vector, where you have first character in the first position and second character on the second position, and so on. This is what you see. Okay, that's not bad. Actually, it might work, but the trickiness of languages comes again, because maybe it's just you would need like so much data to learn something meaningful from this representation. But it's not bad per se. So I would say it's in good direction. So let me try. Oh, okay, we're gonna work with words. We don't go to characters yet. We might use characters later on, but let's just start with words because there's so many of them and they have meaning. Characters don't have meaning, like characters are characters. If you combine characters, you don't get a meaning of a word, right? Characters are like a byte or color, but if you combine characters, yes.
Image processing networks, we also don't say that's a head, and we say that no.
Yeah, but
Like
yeah, fair enough. But I'll come to you later. Sorry, yeah, no, you want to understand? Okay.
So the tokenization we speak of is a semantic operation on the data. So it's not non-trivial. It's not just pre-processing.
Okay. Yeah. So we'll be talking about tokenization, but the difference between computer vision and language is that, as we had this example, I guess, in lecture 1, the trickiness. Like in computer vision, you have a color of a pixel, and it carries the meaning of that, while character doesn't carry any meaning. The word carries a meaning which you induce on that word, but by itself, it has nothing. Like it carries no meaning. So that's why it's hard, if you take characters and just say, yeah, I'm gonna just split them characters and call it a day, like pixels. That might work, but not really. So maybe you need some better units which are words to start with. Okay, if maybe we can take it offline. Okay, sorry, yeah. You see here. Oh, this is so wrong. This is here. You see, this is wrong. There's no white space. Yeah, sure. So, but typically, let's come to it. What is a word? So, we're gonna start working with words. We might come to characters, but this is not the first choice for many reasons because of the compositionality. Word has a meaning. Character has no meaning, and we want to understand meaning. Doesn't make sense? Character has no meaning. Like A. No. Very bad. Oh, sorry. Bad. Wow. Yeah. Okay. It was a bad movie. That's difference, like in perception of things, like how we understand. Yeah.
Question. We want just one vector for the whole text.
Yes. Yes. Because in supervised machine learning, you have the sort of example or instance or sample. Maybe an example is the best word. Is one vector of features. So one vector and a label, which is 0, 1 in our case. Okay, so this is just one huge vector for the whole text. All right, so what is a word? Yeah, well, we're no linguists, so they have different answers. But let's put a simplistic definition. So let's say words are a sequence of letters separated by white space. Okay, so it gets you very far. This is fine. This is like working definition is fine. You take a text, split it into white spaces, and you call it a day, and you have words. It will work most of the time. But then you have a question, okay, well, what's the difference between here dog and dog with question mark and dog with dot and so on, like misspelling errors and stuff like. Are these different words? Okay, so no, we have an issue, so we have to fix it. Okay, let's say now a better definition: words are separated by white space or punctuation. Okay, so this is even better. And the process of splitting text into words is called tokenization. So we split text into a thing called tokens. So when we talk about a word, we typically mean a word in a dictionary. When we talk about chunking text into words, we're talking about tokens. So if I'm going to ask you how many tokens are here, you just cut it by white space and punctuation and you get me like 725. If I'm going to ask you how many words are here, if we clarify what we mean by this, token is kind of clear, is the chunk. If we say word is a different entry in vocabulary, then you would just basically count how many times each word appear. Okay, so this is like distinction between word and a token, but it's not cut in the stone, right? I mean, this is something we we agreed upon like as a community. So, but the tokenization splits the text into tokens based on white space and punctuation. In English, the job is the tokenizer is quite simple, right? So if you just look at all this text here and apply splitting by white space and punctuations, you get the tokens pretty easily. A, matter of debate among linguists, comma, answer, not, and so on. Nice. However, there's languages that don't use white space sometimes, and there's languages that use no white spaces at all. So does anyone speak Chinese here? I don't. Do you speak Chinese? Okay. Yeah. Is it the same? So there's no white spaces. So you have to understand the language in order to tokenize it. A tough job. Okay, so you don't wanna write a tokenizer for Japanese to begin with. If I ask you to write a one for English, easy job. Okay. Any questions? Okay, cool. So we have the tokens, and then, well, it doesn't stop here by tokens. So we have the symbols here like cat and capital cat. They have the same meaning, but are they the same word? Yeah, or maybe like in New York, yeah, it has a meaning because it's compositional, but it's two words or one. I mean, should it be two tokens or one? So yeah, we distinguish between words and tokens, and the output of the tokenizer as a token, and the meaning bearing units as a word. So this is what I said on the previous slide. Basically, something which we can find in the vocabulary would be a word, and something which is output of the tokenizer as a token. And they mostly overlap, but not always. And if you remember the example from the first exercise on the rouge, was it rouge or blue? I mean, rouge evaluation of text, and there was this kind of in the library was, oh, and hey, you have to pick tokenizer, because if you pick one tokenizer, it tokenizes text differently, and you get different scores for rouge than if you take the other. So there could be different tokenizers. Maybe one tokenizer will take this as a one token. Maybe another one would just split it into two tokens by white space. Okay, which one is correct? Which one is correct? I don't think anyone is correct, actually, because what does it mean correct? I mean, it serves a purpose, right? If you are doing linguistic analysis, then if you agree upon what is the definition of a thing, then you might say things are correct. But here is just operational definition. We say, yeah, let's cut it into pieces and it will make our life easier. Is it correct? It depends. Okay, so I don't think one of those is correct. They have pros and cons. Okay. So, and the story is even more complex than that. Okay, then just, yeah, token and word, we're gonna use them in the same way. So if you're a linguist, don't crucify me. Okay. Now we have something which we call a vocabulary, and this is kind of, I guess, a standard definition. So vocabulary is just if you take it from the bookshelf, it's a Duden, it's a vocabulary, so you have a list of words. Okay, how many words are in Duden? Well, many. I mean, depending on the version of the Duden, mine is like that thick, so could be up 200,000 or something. Okay, so typical words are in a vocabulary are from 20,000 to 100,000 words. How do you create the vocabulary? It's also up to you. So you can either say my vocabulary is exactly Duden, or anything else like a Cambridge vocabulary of English, and all words which are in the vocabulary, they exist for me. And if there's a word which is not in the vocabulary, it doesn't exist for me. It doesn't get you much far, very far if you're, for example, doing tokenization on Twitter. I guess like half of the tokens in Twitter you don't find in Duden or in any vocabulary whatsoever. So the clever idea would be you build it by tokenizing your training data. Okay, so you take your training data, you tokenize it, and from whatever you collect, you build your vocabulary. You just put it into a set, and then and that's it. And you might want to store this list. So here is an example of vocabulary, which is basically a list, and each word has a unique index in this vocabulary. Okay, so if I took an English text and vocabulary of size 3,000, and if I learn it on some text, I might end up with a vocabulary of 3,000 words. So it's pretty straightforward. Typically, you have like 50K or plus. And you learn from data. Okay? Any questions? Good. So this is vocabulary. Now, we come to a clever solution. One of the clever solutions, which actually works pretty well in practice then. And it's called the average back of words. So let's have a example sentence, a cat said. It's a stupid sentence, but it serves a purpose. So a cat said, actually the real sentence which is used by linguists is a cat sat on a mat. Sounds super British. I don't know who came up with this example, but it's been used over and over, so I just adopted it. So a cat sat, whatever the cat was doing. Now we have this vocabulary, which we created from the training data, or we took it from Duden, doesn't matter. And now for each each token from the input sentence, we're going to tokenize. So these are our tokens. For each token, we look up its position in the vocabulary and create a vector where we take 1 at the position where the word is, and everything else will be 0. So it has a name, and it's called a one-hot vector. Why is it so? Because all positions in this vector are called like 0, and only one position is hot, so-called 1. So I think it comes from maybe electrical engineering, where 0 is cold and 1 is hot. I don't know. I mean, if anyone has a background from electrical engineering, that's maybe where the terminology comes from. But this is one hot vector because just one position in this vector is hot. So to say it's 1. And this is exactly the position where the actual word is in the vocabulary, okay? So for example, if we have A at position 1, the representation of this word would be a vector where the first position will be set to 1 and the rest will be zeros, okay? The same for a cat. So we had cat at position 852 at the vocabulary. So we will have a vector full of zeros, and then there will be just 1 at position 852, and the same for set, okay? Does that make sense? So basically, we are turning each word, each token, into a vector full of zeros, except for one position, which corresponds to the index of the word in the vocabulary. So what would be a vector for word abandon?
All zeros, and then the second one would be a 1.
Exactly. It will be all zeros, and it will be 0. Then the second position, so abandon, would be represented as 0. Then on the second position in the vocabulary is abandon, so it's going to be 1, and then zeros, and the rest is all zeros, okay? It should be straightforward, but I just want to double check that everybody's on the on the same page. Okay, cool. So we have this. And then the way of representing the full document, which is comprising of 3 tokens, is to take these 3 vectors, sum them up, and take the average. Well, basically taking the average. I mean, you sum up and divide by the number of the vectors in there, okay? So this is the fancy formula here. We take all these vectors, so we take A vector plus cat vector plus set vector and divide by yes, 3. Why? Because you have 3 words, 3 tokens, right? If you had like a cat sat on a mat, how would you create it? A cat sat on the mat. How would you compute the average back of words? Yes.
You would add all of the vectors up and then divide by 6.
Plus, 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 plus. It's unreadable, I'm sorry, but you get a gist. Divided by 1, 2, 3, 4, 5, 6, exactly.
But then in the spec of words, you lose the complete ordering of the sentence.
Exactly. In the back of words, the big advantage of back of words, you completely lose the ordering of the sentence. Let me just see if I have. Oh, actually, I have an example on the next page. But anyway, yes, because is there any difference? So yeah, a cat set is kind of you can do it in different ways. Like a sad cat, yeah, but it should be said like a sad cat. Like with D. Traurige Katze?
No.
No.
Set a cat.
Set a cat. Set a cat. Yeah, and if you ignore a question mark, right? Yeah, set a cat. Well, did a cat sit? Yeah, it's weird, but okay. Yeah, but serves the purpose. But we might have better examples, maybe. But okay. So what's the difference between these two in the average back of words? What's the difference?
Oh.
There is no difference. They are equal because the ordering doesn't matter. That's what you said. Exactly. It's a big disadvantage. So why do you think the word back comes from? What does it mean? Why is it back of words? Exactly. A back is under a set. You throw everything in a back. I wouldn't say it's a set because it's a multi-set because you might have multiple occurrences of the same word. You throw all the words into the back and take the average. You don't care about the ordering. So it's a back. You throw everything in there. So obviously it will fail for many linguistic things. What will be the? Do you have any idea, like any example where it fails? Like what is super bad about ignoring the ordering of words in a sentence? Yes.
I would imagine that this would be difficult for sentences like the movie was not bad or something like that.
Okay, the movie was not bad. So what did you use here? It has a like linguistic meaning or not linguistic. Negations. Negations saying not bad and saying something, oh, it was not surprising, it was so bad. Right? You have like different orderings, but the meaning will be completely lost, So because yes.
I prefer numbers over letters, where you can.
Yeah, exactly. It's even better. I prefer chicken. I prefer chicken over vegetarian. It's very much different. I prefer vegetarian over chicken. You end up with very different outcomes of the evening, right, in the restaurant. So that's another example. Ordering matters. In language, ordering matters. Like it's a sequence of tokens we're talking. But for document classification, empirically, it's not a bad baseline, actually. In many cases, it just works. You throw things into the back and it gives you something. It will fail on these examples, like negation, ordering, or, and stuff like that, obviously. So there is one advantage of that is, what is the advantage? Okay, maybe I have okay, here's an example, a cat set, exactly. And here we computed the actual outcome. So sum up and divide it by 3. So this will be representation of a document, a cat set. It's a vector. Okay, what is the size of the? So yeah, maybe let me see. Yeah. Okay. What is the advantage of having back of words representation? So having this like that, and now imagine you have a set of documents, and they have differing lengths.
The advantage we have the output vector we have is always the same dimension.
Exactly.
That's what we need because let's say we just give every word a number, if then for the example with the short-sight redemption would have a dimension of 500.
Exactly.
And if somebody comes with a review, loved it, it would have a dimension of 2. But we need the same dimension for everything because we don't have that. We can't build a function.
Exactly. So our assumption was we need some input dimension which is fixed for our function. We want to learn the parameters of this function. And we decide how big this input dimension is. So we need to fit everything. This has like 800 tokens. And the cat set has 3 tokens. But the advantage of the average back of words, they're going to end up with the same dimensionality of the output. And the dimensionality is going to be, again, what? What is dimensionality of the output we're using in backup words? We had it on the slides. I'm just, sanity checking. Yes.
The size of my thinking.
The size of the vocabulary. So we're projecting everything. These both will be projected on a vector of size of the vocabulary. This is cool. So the input size will d in is actually the size of the vocabulary. Yeah, that's fine. That's not bad. Could be 50,000, but why not? I mean, nothing is preventing us working in 50,000 dimensional vector space. That's okay. It won't break. You look puzzled, yes.
Also store words we don't know.
Good question. Okay. Very good question. So what do we do with words we don't know? We call them out of vocabulary. So this is the example that when building the vocabulary. So, okay, let me start. We come to that exactly. So, but how is the distribution of words in a language? So distribution means like how often words occur in how often they occur in a corpus or in speech, right? So how many words you think you need to understand in a language? You need to know in a foreign language in order to read something. How many words you need to understand, roughly? So in German, it's for me it's a foreign language. So if I excuse me. So for learning German, you need roughly 200 words if you wanna read das Bild, and you need 500 for FAZ, something like that. I read it somewhere, to be honest. Like the vocabulary is much smaller because you're mostly using very small amount of words, and the distribution is some sort of I would say exponential. So here, D or A or I don't know, I and M and so on will be high probability of occurrence because you're using it all the time. And here there will be like weird words such as, for instance, whatever it was, something which is not used that often. Okay, so this is called the tail. So the tail of rare words. There are rare words which you don't use that often. Which means when you're building vocabulary, you might actually use the most frequent words. So let's say, okay, 3,000. This is good. This is enough for me, or 30,000. And you just ignore the rest. But then, what do you do with the unknown words? I mean, you can just ignore them, or typically you add the so-called special token U and K for unknown words. So our example, we have the most common 3,000 words, and we add the U and K into 3001. Okay, so we add unknown word to the vocabulary. So anytime we have here a cat said, what was the word you said? Aparosacalizes, something shorter. Okay, no, something. So some rare word which is short. Say again. Alphanumerical. Okay, alphanumerical. It's not short, and it's BLMPF. BLMPF. Is it a word? Yeah, it could be. I mean, on Twitter, like BLMF, I BLMF that. I don't know. Maybe it's a made-up word, but it's very rare. So a cat sat on a BLMF, right? You don't know what a BLMF is, so you say, okay, it's gonna be. I'm gonna map it to unknown, and then it's fine. I mean, you can take it into account, or you can just ignore it. It doesn't matter. So sometimes it doesn't matter. Sometimes it does. Okay, here for the classification. However, how do you translate a word, an unknown word, in machine translation? This is interesting. Shall we make a break? Or in maybe 7 minutes? Let me just, how many, blah, blah, blah. Okay, just 5 slides and we make a break. Okay, cool. So how do you, if you have unknown word, how do you translate it? Okay, I have an example for unknown words. It's names. So for example, a cat sat with and a name, Mr. Name. Give me name. Say again. Bloemf. It's very weird name. It's very it could be like Dutch, but I don't know. With Mr. Habernal. I don't know. Maybe it's not it's not really common. I mean, the names is not really common. So a cat said with Mr. Habernal, and Habernal is not in a vocabulary, obviously, so it's not really common. So you would maybe replace it with a unknown. Now, if you want to translate this sentence, a cat said with Mr. Habernal, and you have unknown word, what do? So you maybe start translating word by word, and then you reach the unknown word. What can we do?
Just keep it.
Just keep it, exactly. Just copy paste it from the input to the output. So there is no issue of that. Yeah, you can keep that. So but we might do something better than just plain tokenization, and we might go into what you I have actually one point with the characters. So you propose a splitting into characters and have an array of the characters. And the issue would be you would have for every document you would have a different length of the input. Yes, yeah, but the yeah, so you can cut like in stone, saying, well, my document's length is maximum 5,000. That's what I mean with transformers, exactly. Yeah, yeah, sure. That's what's happening with transformers. There's a design choice. You can do that, and maybe we'll come to that. I mean, basically, what you're proposing is not really. But say again. They do have a max length. The max context length is a parameter. No. I mean, the transformer works over a fixed vector, and it's fixed. No, you have fixed. So sorry, we're getting way too forward. But a transformer is exactly what you say. You have to set the size of the input, which is long, but it's not unlimited. In BERT was 512 characters. Sorry, tokens. And GP is the same thing. You're limiting your token, like the span, the attention span. You're moving by character, by words, but it's limited. We'll come to that. Sorry, people. Yeah, you can do this absolutely. Like, sure, that's not a bad solution. So the characters might be maybe too fine-grained. The question is like, do they have the properties we want them for classification? Maybe they're just too fine-grained. So maybe there's something in between. Maybe there's something between words and characters. So we're gonna use so-called subword units, and one of them is so we're gonna go deeper into the words. Excuse me. And the first one is going to be called byte-pair encoding. So the words in the corpus are actually first split into characters, and we're going to mark the original spaces with a special character, and this will be the initial vocabulary fee. So what we're doing is we take every character we see in the corpus and putting it into vocabulary. So the vocabulary is consisting of just characters, which are in the training data. So mostly it will be like alphabet, maybe numbers, and maybe if you have like different alphabets, will be characters from different alphabets. If you're like multilingual corpus, so it could be Chinese characters, Japanese characters, and stuff like that. Then what we do with the vocabulary, we take the most frequent pair of characters, merge it together, and add it again to the vocabulary. So we're basically saying, well, things that are very often together, like the two characters which are very often together, should be actually a word in the vocabulary. So you're going to merge them and add to the vocabulary. We'll have an example on the next slide. So we just repeat this. And obviously, each of these steps will increase the size by 1 beyond the original sort of inventory of single characters. With byte-pair encoding, then you can tokenize a text in the worst case, So in the best case, you will find a word in the vocabulary because you kind of, through the merging, you came up with a word. Let me start maybe with the example and talk about this later. So let's have a toy corpus. So we have a sentence, this fat cat with the head is in the cave of the thin bed. It's a weird sentence, but serves a purpose. So we tokenize and have this special character as a white space character and keep it there. Now, we put all these characters we find here, so TH in the vocabulary. So the vocabulary is going to be TH, I, S, and so on. So all the characters here. Now, we're going to find which is the most frequent sort of bigram of characters. And this will be, so we just, compute all these bigrams and their number of occurrences and say, oh, TH is actually the most common one. So we're going to merge it here and add TH to the corpus, to the vocabulary. Excuse me. Then repeat again. So now in this text, what is the most frequent bigram of these things? And we find that actually, oh, AT, and so on here. So there's a multiple here, AT. So AT is 4 times the most common. So we're going to merge AT and add it to the vocabulary, okay? And then replace again in this corpus. So we're continuing here. Now, let's say we merge TH and E because we have multiple occurrences. So TH and E occur together here and here. And voila, well, we have an actual word which we know and add it to the vocabulary as well. And we repeat as long as we want, or as long as we, kind of exhausted all the options or reach the size of the vocabulary, whatever you want. And we end up with vocabulary which has the, excuse me, the characters and also the words. Because some things occur most likely together, so it seems like they are words. The thing is, once you have this and start tokenizing text, well, if you don't find a word, you will always find something smaller, which is called subword. Right? So if you had a word, let's say Habernal, well, it's not in the vocabulary, but in the worst case, it will be represented as characters in the worst case, because the characters should be all there from the alphabet. And maybe some syllables will be there and stuff like that. Ah, okay, that's interesting. Does it make sense? Okay, so it helps with out of vocabulary. Also in machine translation. So I think we're through. So there's actually one better variant of this, and I think then we're done. And it's basically something which is used more often, I guess. It's a sentence piece. So it's a variant of byte-pair encoding. And the byte-pair encoding here has a problem because it starts with the splitting into these characters, and then there's some arbitrary decision on these white spaces, which are replaced by special characters. So you need to tokenize the text first, which means if you have the text tokenized by byte-pair encoding, you cannot turn it back into text as it was originally. Because if you have say something like I was, comma, it's a very stupid sentence. I know. I was, comma, something. Well, anyway, once you tokenize it, so there is no white space here, right? I mean, there is no white space before a comma. Once you tokenize it, you get I was, comma, something, and so on. But then you cannot turn it back into this original text because you lost the information about the white space. I mean, you don't know whether here it was a white space or not, because if you had a sentence, I was white space, comma, white space, something, you had the same encoding here by the tokenization. So you cannot recover the original text because you lost the information by just splitting by white spaces and taking this arbitrary kind of thing here. Okay, does it make sense? Okay, so that's maybe bad. We want to keep that. We want to keep the original text. So that's what sentence piece is doing. They introduce a new kind of special characters like this double ampersand. But basically, if the word is being split here using, so sentence piece is very similar to byte-pair encoding, but if a word is split in the middle, exactly. So the example here would be the same for splitting a word in the middle. For example, my surname. If you split it into tokens, you don't know whether they were stitched together in the original sentence or not. So that's bad. You want to kind of make the word up again from the tokens. So here, if the word is split into two, there's these characters just signaling that you should kind of stitch them together. So they were stitched together in the original text. So here, the sentence was the relationship between Obama and Netanyahu is not exactly friendly. So it's some text from the news from, I don't know, 15 years back. But here we say we see a name like Netanyahu, which wasn't, Obama was in the vocabulary. Obviously, if it was trained on some web data, Obama is something which appears much frequently. So you learn Obama, but it didn't learn in a way Netanyahu. So it split, but it learned the subword units, and it split Netanyahu into these three subwords. But by signaling this ampersand, we know that we have to stitch together and get a word Netanyahu. Okay, so this is a lossless tokenization. You can reconstruct. It has all the information to reproduce the normalized text. To reproduce the normalized, all the information to reproduce normalized text is preserved. Exactly, it preserves all the information. Okay, so sentence piece is, excuse me, a better choice for tokenizing subword units. So lesson learned. We have tokenizers. We want them to, we have a text. We want to get a back of words. We use tokenizers. Typically, the simplest thing is back of words. But we learned also there's better tokenizers than just back of words because they work for unknown tokens, and they just kind of get rid of these unknown tokens. So byte-pair encoding and sentence piece encoding. Okay, any questions to the tokenization? The byte-pair and sentence piece will be more important later on in transformers. Somebody forgot glasses here. None of you. Okay. Anyway. So if you don't have any question, I would say let's make a 10 minutes break or shorter. What do you want? 5 minutes is enough? What was it like? Short break. Okay, cool. So 5 minutes. All right. So 9:40, we'll continue. All right. Ja, was es reicht. Okay, so now, okay, what do we have? So the task was to the binary classification. Cool. We understood that we need a vectors, and we have these functions, and we know how to represent text as a vector. This is cool. Back of words, average back of words, simplest way. So we have vector. We have the label is 0 or 1. So we have everything covered. We have training data. Okay, cool. How can we build now a simple binary text classification? So again, binary classification is a function. So we have this linear function, which takes a vector. So sanity check, what if we have vocabulary of size 3000 was the size of this vector? 3000. Yeah, exactly. That's why it's called sanity check. Yes, we're here. Okay, we're back. So, and this will be a scalar. So 0 or 1 in effect. But it could be, the output could be anything, but we want it to be 0 or 1. So we said, we're gonna use a linear function. So we're gonna take the input vector. So it's not gonna be an object in 3D anymore and projecting onto one spot on one dimension. It's gonna be 3000 dimensional vector, but everything will still apply. I mean, you can multiply a 3-dimensional vector by a matrix or a vector actually as a dot product to get get a value on 1 dimension X. And then there's some bias thing. Okay, so how does it work? We multiply in this dot product, we multiply each with other and sum them up. Okay, so this is the linear function we're using. Now, because you know already that in order to do so, we're using the computational graph, where each function has to have, well, we know how to compute the output. So this is how we compute the output of this function. And then we need derivatives, partial derivatives with respect to the arguments of these functions, or this function. And we are especially interested with respect to parameters w and b. We don't care about partial derivatives with respect to the input. Why is it so? Why do we care about just the parameters? Why don't we care about the inputs? Yes.
We want to minimize the error regarding the parameters. The input.
The input.
The input x is we want in the end we want one function given a weight vector w that for all inputs we have give at least
you're right. So for us, actually, the input is given, it's constant. So we cannot optimize anything in the input. It's constant. We want to optimize or change the parameters such that some error is kind of minimized. So we're optimizing, so to say, only on the parameters because they can change. This is given equals constant. So you cannot change it. So it doesn't make sense to make any partial derivatives with respect to constants. That's the real deal. Like why it can't work. I mean, you can try. Well, you can do partial derivatives with respect to everything, even like constants, and it will give you something. But we're interested in optimizing the parameters, finding the best parameters. So we're optimizing the parameters. So we are projecting from a space of vocabulary into one. But what is the space of the parameters? So, okay, this is interesting. So now let's say this is 3000 size vector. But what is our space in parameters? How many dimensions are we optimizing in? So we have parameters. Remember, I mean, optimizing functions of 2 dimensions is as like we have surface, and we find, the minimum in the surface, like banana function, 2 dimensions, and you find the minimum, okay? How many dimensions do we have here in which we are going to be looking for a minimum? Is it going to be 3000? Is it going to be something else? And if it's going to be something else, what? We are optimizing the parameters of the function. How many parameters does this function have? I'll see you, I'll get you, I'm trying to find someone else find this. So you first and you second, okay?
3000 parameters of the weights plus the bias parameter.
So it's going to be 3001, exactly, because it's going to be 3000 parameters of the weights, and the bias is also a parameter. So we are in 3001 parameter space. So basically, they don't have to be the same as the input. Like input could be like 10 vectors, sorry, vectors of size 10, but if you have a very complicated function, you're optimizing in much larger space. This is a very simple function, but if you stitch it together in like neural network, you might have billions of parameters which you're trying to optimize, but the input will be always the fixed 3000 or whatever you choose. So just keep in mind, like these are 2 different spaces. Like one is a space of the input, but we are optimizing in the space of the parameters. So this is what matters. So imagine how do you optimize in 3001 dimensions. You cannot imagine 3001 dimensions. I mean, you can imagine maybe 2, and then you see the surface kind of like mountains, but in 3+ dimensions, you can't really visualize that. So it's going to be some sort of complicated space, but we're using the techniques which we developed before for finding the gradient, right? I mean, it doesn't matter how many dimensions you have, so you can do anything you want arbitrarily. But we just need to make it differentiable. So this linear function is differentiable. And I have the answer here already, but you would come up with this as well. So the derivative of this function with respect to, let's say, W1 is going to be, well, it's constant times W1 plus some other constant. So it's going to be the constant of, which is a multiplied by W1, okay? Everybody knows how to do this partial derivative? More or less? How we end up here? Who doesn't know how to do this partial derivative? How did we end up here? That's fine. I mean, that's okay. I mean, you can say I don't know. You don't know. Okay. So you have y equals to ax plus bz plus cw. What is partial derivative with respect to x here? How do you do that? So these are constants, so it's going to be 0. This is constant, it's going to be 0, and forget it. And this is going to be a times x. So the derivative of a times x. So this is 1. This is a. Is going to be a. This is what you understand. Well, this is the very same thing. It just looks differently because x1 is a constant, and all of these are constants, and these are the variables we are optimizing. Okay, makes sense? Cool. The same for b. So the derivative of b with respect to b is 1. Okay, so we know, right? I mean, derivative of b, if y equals b, and dy to db is 1. It's a constant. Okay. So we know the derivatives, so this is great. So we can basically build this and put this into our conditional graph and run backpropagation to find a gradient of this function. That makes sense? Everybody's with me? Okay, cool. So the thing is, we want to output 0 or 1 or something in between, but because we don't want to like, so how can we interpret, like, if our function outputs 522,23, how do we map it to 0 or 1? Well, we want a function. So this linear function has an unbounded range. Basically, this can output anything from -infinity to +infinity, right? It can. Why not? Do you agree with me? Okay. So, but our example labels are 0 or 1. So we want maybe to kind of push this range of this function so it's between maybe 0 and 1. So without looking up the answer on the next slide, I just wanted to make sure that we are understand, we are coming there. How would you, so let's say you have let's say a number y is in -infinity and +infinity. We want to make it into 0, 1. What do you need to do with this y? Is there any function that takes y, which is anything, and squeeze it into 0 or 1? Any idea? What could be a function that takes a number, which is any number, and produces something which is in the range of 0 and 1? Yes.
Well, if it's 1, we map it to 1. If it's something else, we map it to 0.
Oh, if it's, okay, you would say if it's 1. If 1, then say it's 1. If not 1, it's gonna be 0. So what if we have answer which is just 1.0000001, which is almost correct, and you would say, oh no, this is going to be 0. Yeah, I don't think, yeah, why not? I'm afraid it won't fly.
But the thing you want is like you want the nearest, but I didn't get that from your question.
Yeah, that's fine. I mean, yes, sure. I mean, this is a solution which kind of answered the question, but it won't work for the problem, which is we have some output, so we map we map something, we map an object or something on a line. We map a negative review somewhere on a line. We map a positive review somewhere on a line. And everything will be projected on a line because the output of the function is a scalar. So it will be always projected somewhere on a line. But our gold labels are 0 and 1. So we want, what we really want is that it gets projected as close as possible to 0 if this is negative, or as close as possible to 1 if this is positive.
An equivalent mapping in a Python space.
Yeah, I want to map unbounded range into something between 0 and 1 at best. It could be also minus, but between 0 and 1 has a nice property because what is between 0 and 1 always? Something is always between 0 and 1. Something, some concept in mathematics. Probability is between 0 and 1. So maybe when we map it between 0 and 1, it gives us also the probability of being 0 and 1. That would be also like a bonus. That's why we want to put it here. So is there a function that takes anything and put it into 0 or 1? Do you think of any function? Is there something that we might think of? You on the back, yes. Oh, the sigmoid function. So you knew a sigmoid before? Okay, cool. That's the answer, exactly. There's a sigmoid function. If you would think maybe a little bit deeper, you would end up with something like, okay, everything negative should be positive. So something like with maybe exponentiation of something, e to the number, and maybe something else. You would end up with a sigmoid after some deep thoughts, I'm pretty sure. So we have this function, and it's called sigmoid function, or so logistic function, which is, well, I mean, this is one form, this is the other form, these are equivalent, which takes any number, real number, and produces any real number, but it will be in the range as we exactly want, like between 0 and 1. So everything from minus infinity to plus infinity will end up between 0 and 1. And that's what we want. Okay, so this is how the sigmoid looks like. Does it make any sense? It's a nice function. I mean, we could say also before, well, you know what? So everything here, which is, if this is smaller than 0, it's going to be, or maybe smaller than 0.5 is going to be 0. And if this is bigger, 0.5 is going to be 1. We can take like this sort of a step function, just decide like that. We can do that. The disadvantage of this sort of step function would be what?
Cannot get any numbers between 0 and 1.
So you don't get the probability. Yes, you don't get the probability. And the second one, because we want to put it into our computational graph and make a stochastic gradient descent and sorry, the backpropagation stuff. What would be a problem with this function?
Because it doesn't really show any functions, just like this.
Well, it would be exactly. It would be this and this. So what is the issue here if you want to do the minimization of this function? What's the gradient of this function?
Yeah, 0, and then you can't really find the minimum because the minimum is everywhere.
Exactly. So it has a zero gradient. It doesn't tell you how far off you are. And also here the gradient, so it's not a continuous function, so you have to make arbitrary decisions with the gradient here in between and so it would work, but it's not nice. So we have a smooth version of this step function. Well, you look, it's sort of like a step function, but it has this beautiful knee in between. And of course, the advantage is that you absolutely can differentiate it. So you have the derivative, okay, of this function. So this is property. Okay, so sigmoid function, your new friend. You should know this. Either this or this, but you should know a sigmoid function. Like really remember. Okay? It's a backbone function. So it's a nonlinear function because it's squeezing a little bit of space. So everything will be mapped, from the linear space of the projection will be mapped into this kind of between 0 and 1. And the more negative the number will be, the more closer to 0 it will be, and the more positive it will be. Oops, excuse me. Oh, no, stop. I got crazy, sorry. The more positive it will be, it will just go to 10 to 1. Okay. So, okay, here's the derivative. So if you do like a little bit of gymnastics and a little bit of calculus, you will end up with derivative of this sigmoid. Oh, actually, this derivative of the sigmoid is also very nice. Why is it nice? Why is this derivative of the sigmoid is so nice from the computational perspective? Yes.
Because it contains itself and constants.
Yes, because you already, if you do this backpropagation thing, you need to compute it this value anyway. So there is no extra computation of doing the derivative of this sigmoid. Oh, this is cool, because if you do like the proper caching and the propagation, you know this already. This you computed before for the parent functions or somewhere else. You computed just once, forever, and then just reuse. So there's no other exponentiation or so. Yeah, I mean, you just run the sigmoid once, but then this is like basically reusing the value itself. So it has really nice derivative as well. Okay. So now what we're gonna do. So this is a combinational graph. So when do we need to finish, by the way? Was it like 10:20 or something, or 10:30 or 10:15? 10:30. So we finish before 10:30. Like, yeah, okay, I'll try 10:20, but let me see. I don't want to rush on this, but let's try. So, okay, so here let's see what we have here. Here we have a function which is basically our Lagrangian model. So this is what we are trying to build today. Let's look at this. So this is the linear mapping, right? This is what we have. We take the input vector, multiply by parameters by this vector of weights, so-called, and so this was weight, and this is the bias. Oops, bias. So we multiply the input. So here's our input. Basically, I created this combinational graph here. So the green circles are the trained parameters, and gray are constants. So this is a constant. This is given, right? Constant. And this is what we want to optimize, like change, minimize. So we have the vector W and bias B. So we're multiplying the input by the weight matrix and add the bias. So this could be basically a scalar node. If we, if you remember what we did yesterday, we used like scalar node has some parameters and outputs a real number. Okay, so we could implement it basically in the computational graph as a node. So this is what we can do. And then there's another node, which would be like a sigmoid node, which basically takes one parameter and outputs the sigmoid function. So the sigmoid is again 1/1 plus a to minus x. Or let me put just something as t, like, because the x might be misleading. This is not the input of the network. It's like t. So right. So if you implement this with the partial derivatives and stitch together, you have the Lagrangian model. That's all you need to do. There is one thing you need to implement is the linear projection. So we know how to compute the output because it's just multiplication of two vectors and addition of one number. We know the partial derivatives because we computed them just right away. It's that's what we are confused about, but we clarified it. So we know the partial derivatives as well. And this is the sigmoid function, which takes a real number between -infinity to +infinity and squeeze it to the range between 0 and 1. And we know the partial derivatives of this function too. So when we build this, now we don't talk about the weights. I mean, let's say the weights are now given somehow, random. If we have this for now completely random, so it means it didn't train anything, still, I take any input document, text, turn it into, let's say, back of words, which gives me this vector. I can run it through this combinational graph, this function, and I'll get a number somewhere between 0 and 1. This is it. This is the Lagrangian model, nothing more. It's a linear because we have linear projection here. and log linear because it's in log space. So it's linear in the log space because of the sigmoid. But basically, we first multiply the input by some weights and then some bias, so some linear projection. And then by the sigmoid, we squeeze it into 0 and 1. Okay? Any questions? So do you think you could implement this? That's a question from me to you. Do you think, I mean, we can basically code it up next week, given what we have so far? And given that if you get better familiar with what we have so far and understand the nitty-gritty details, you'll be able, I'm pretty sure you'll be able to code it. I'm almost sure, I'm certain that when you play around with the pieces we had so far, you'll be able to build it and really, really understand it as well. Like why you are doing the derivatives. Yeah, because you want to find what? You want to find, maybe later on, you want to find a, let's this be partial derivative of the sigmoid with respect to W1 and partial derivative of the sigmoid with respect to W2 and so on. Yeah, because you want to optimize these things. This is the gradient and we need to find the derivatives. And if you code it up in sort of the computational graph with back propagation, you will find it very efficiently. Okay? So if you think we should code it up, let me know. If you disagree, let me know as well. Okay? I'm planning to do so, but you have to be prepared. Okay? So which means like maybe watching this again, reading this again, or playing around with the things we did before. All right? So now, okay, well, what the sigmoid is giving us is the real number between 0 and 1. But remember, we want to predict 0 and 1. So now what we're saying is, yeah, now let's take a decision. So because our classifier should predict, yeah, this is positive or negative. So we just say, yeah, if it's bigger than 0.5, it's going to be positive, and if it's smaller, then it's going to be negative. But also, as we kind of had this nice representation, this gives us the probability that the prediction is positive, given the features. So this is the probability. If I see the features or the text, and I'm outputting the sigmoid out of it, it tells me, oh, 0.75 probability of seeing 1, or 0.1 probability of, this is the true label. Okay, so this is the probability. This is some natural representation of the sigmoid thing. It gives you some sort of probability. So if your model outputs 0.51, you would say, yeah, it's positive, but it's not really certain. So maybe I should be somehow, suspicious about its result. The thing is, mostly it doesn't work. So mostly the models are so confident saying like, yeah, this is like 99% probability positive, and it's just super wrong. So if you want to use it for some sort of explanation of the models, it will get you somewhere, but it really depends on many things. So it's not a way of explaining predictions, but it's really helpful to give you maybe some confidentiality. Okay. Any questions to the probability interpretation? Okay, cool. So let's finish this. There's just a few slides. We're there because we know everything we wanted to know. Okay, so we haven't talked about the loss function, and this is something, yeah, because what we have so far is saying what the prediction is going to be, but we don't know whether is it a good prediction or bad prediction. So our model takes an input and outputs a number between 0 and 1. How do you, and can you say it's and you have the gold standard label. The idea is, well, knowing the gold standard label, we also know whether it's a correct prediction or not. And we also know how bad are we mispredicting the label, right? I'll show an example right now. So I'll start with the example and come back later. This is a bad example, okay? Let me start with some super simple example. So let's say our model prediction, which is this y hat, is going to be 0.75. And the true label, label for this example was 0. Can we say, oh wait, first, was the prediction correct or not? No, of course, because we would say it's positive. Can we say something like how bad the misclassification was? Yeah, so how can you do that? I mean, how would you quantify the error?
I would quantify it by how far he went over the 0.5. So
which means?
One, it would be worse than if it predicted maybe 0.5.
So how would you do that? How far? What does it mean? Like a distance?
Yeah, maybe distance or square.
Okay.
Distance.
Well, y squared distance. Let's start with distance. Okay, so we would say maybe y hat minus true label. So it would be 0.75 minus 0, 0.75 mistake. Okay, cool. Maybe what if this were 1? Let me just keep this. Okay. What if this were, now the true label is 1 and the y hat again is 0.75. Okay. So now we would, if you use this method, which you didn't propose, but I'm proposing it as the most simple solution, would be 0.75 minus 1, which gives me minus 0.25. Yeah, so how can we fix that? I mean, I don't like this zero error. Negative error is kind of bad. So what was the best thing to fix that?
You could just make it positive. Take the
Absolute value. Okay, let's do this. So we would, this is done, and here we would have plus. Okay, that's better. So we quantify the distance. I mean, it's basically a distance on the xs. You know, this is distance between 2 points, and if you just subtract them, that's fine. Okay, cool. Well, this is not bad, and I think it's basically one of things to solve it. But you said like also square distance. So what did you say it? Somebody said like squared. You did say it. Why did you say it?
Because it would punish the model harder if it does like the more extreme mistakes.
Okay, it would punish the model harder. Okay, so let's make a punishment. Yeah. Okay. Let me find punishment. So, which means if we had a true label is 1, and our classifier here, so C1, says that the prediction is, or the value is 0.4, and the C2 says the prediction is 0.01. Right, and you wanna do what? The punishment. So you wanna punish something. What do you wanna punish?
The mistake is more. The mistake is larger.
So this should be much worse. This should have much more like error, right?
Yeah.
So okay, how can we do that? So if you say like it's squared, so you would say y hat minus the true label, and instead of absolute value, you would say squared. That's what you propose, and that's true, because then this, so it will be like 1 minus 0.4 is 0.6 squared, which is, well, some number. You can compute it. But then this will be smaller than 1 minus 0.01 squared. And that's what we want. I mean, we wanna, so, oops. We want to punish this more, saying like, well, this is much more worse. So this will be like, excuse me, that's wrong. What? Sorry, I just got distracted. Like 1 minus. I got confused. Well, we're punishing like the worst are kind of we're punishing the misclassifications. So Okay, so this is good. And we have a name for it. So we're gonna say it's a loss. So it's a loss suffered when predicting y, while the true label y. So we have this is the prediction and this is the true label, right? So in binary classification, it's a function from a true and prediction into some sort of misclassification or loss. How much we lost on this example, right? I mean, how off we are, how much off we were. So we have a per instance loss, of course. I mean, we are talking about like this is one single instance, right? This was one example from the training data. And we want to define a corpus-wide loss. So because we're training on the whole corpus, and we have the parameters. So what is this thing? How is it called? The Greek letter theta, a capital theta. Yes. So we use this capital theta for just parameters. So no W's and stuff like that. Just theta, some parameters of the function. Okay. So the corpus-wise loss with respect to parameters is basically a loss for a single example. So this loss function, this is what we have here. So we're gonna take for each example, we're gonna do some gymnastics like this, like take the growth label and the output of the function and punish maybe by, I mean, absolute value is fine as well, it will work. So absolute value or squared, for reasons which you might now understand, what is better, having an absolute value or having a squared something? Also gives you something which is much easier if you want to computational graph that. And that is because this will be a function and each function has to have derivatives. And it's much easier to make a derivative of a squared function because it's going to be just 2 times y minus true. Ah, cool. Absolute value derivatives is kind of nasty because you have to deal with the edge cases and stuff like that. So this is this is a nice property. So we take it for each example, and then so if we have n training examples in the data set, then we just take an average. Okay, so we have training data, we have a function, this log linear model or some sort of model, and we want to know how bad is it, like what's the loss on this with these parameters on this function, like what's the misclassification thing. So we run for example this loss function, like this local one, and just take the average all over the entire corpus. And that's where we know, okay, our model in this current state that is achieving some loss on the corpus. Does it make sense? It's not the accuracy. It's a loss, and accuracy is not the same thing. Accuracy is basically counting the predictions equal or not, but loss is more sort of say like fine-grained metric because we're kind of looking into the predictions, and the loss is specific to this function because we know it's in the range and the true label is also in range 0 and 1. So we're making use of this information. So we're taking this the square of that. Okay, so we have this loss per example. Any questions to that? So everybody knows how to compute a loss over training data now. We take each example, compute a loss, and just make an average. So the thing is, now we're coming to the optimization part. Like, okay, we want to do some. Why is the minimization we talk about like that important? Because, well, the training examples are fixed, right? We know like the vectors are given. This is a text. We turn it into vectors, and this is constant. What we are interested in are the parameters of the function, the W's and B's, and maybe other things. And the gold labels are also fixed. So this is fixed, this is fixed, this is, we need to find good ones. We need to find good parameters. So the goal of the training algorithm is to set the values of the parameters theta such that we minimize the loss over the data set. Ah, okay, minimization, I know how to do that. We're minimizing function, and now we know which value are you minimizing. We're minimizing the loss, which means the loss is how far off on average are we from the true labels. So if our classifier is doing, so sanity question, sanity check. Our classifier is predicting everything exactly correctly. So exactly means if this is 0 in the training data, our classifier outputs 0, real number, 0 and 0, not like 0 point something, 0. If this is 1, our classifier is saying 1. What is going to be the loss of this? What loss our classifier will have if it exactly predicts the correct exact numbers for 0 and 1 over the training data set? What is the loss of this classifier? It's 0, exactly, because it will be 0 minus 0 squared or y minus 1 squared. So it's 0 on average, right? Like 1 over n or 1 over n, one of those. Okay, cool. So it's 0. It can't be any smaller because square function is a non-negative. It can't be any, it can't be, so it can be only positive. So what could be the worst loss, the worst ever loss we can get on the training data? I don't know the number, but like conceptually, when will we hit the biggest loss of our model? Yes. The loss should be 1. In this case, let me see, 1 over, no, I think it depends on the size of the data set, because you have like the average 1 over n. No, but we're, let me see, 1 over n. Okay, so you're summing up. Yeah, okay, it will be 1. Okay, in this example, it's actually 1. That's correct. Which means everything will be misclassified. Everything will be wrong. So everything will be 0 minus 1 squared or y minus 0 squared sum and 1 over n. And in this case, actually, it will be 1. It's interesting. I never thought about it. Okay, cool. So what we want to do is punish this and move to this, right? This is what we want to do. We are minimizing the loss to get it to 0. If we have 0 loss, we perfectly learn the model on the training data. Voila. Loss is what we want to minimize on the training data. The question is like, well, okay, if I just remember the training data, my loss is 0, but maybe on the test data, I will just completely crash. I mean, if you remember all the training data, so-called overfitting, then yeah, you will solve the task, you'll have 0 loss on the training data, but maybe if there's something new coming, it's it's another challenge. So the generalization is a challenge, right? But in general, you're trying to minimize the loss. You want to try to learn the function that best mimics the training data. Any question? Yes.
Why do I? Because if I have the maximum loss, I still need to know what I'm doing, because I need to get every answer wrong. So basically, I just have to flip my output to get the right answer. So
well, if you learn something like that, then you're learning basically the task in the wrong way. Yeah, so it's not random anymore. I mean, random would be, let's be very clear. Okay, that's a fair point. I mean, this is the maximum loss, which is not realistic because you're actually learning something and just flipping the opposite. The actual would be everything will be 0.5. So if you just random prediction, right? I mean, you say random for any case like 0.5, you don't know which is which. So this would be like the most stupid model. Yeah, fair point. Thanks a lot for that. Anyway, I don't think we're gonna use actually the square loss. We're gonna use a different loss. But the gist is clear, okay? So everybody's with me. We have a loss on the corpus and we want to minimize it. Okay, so what could be loss function? We came up with the absolute value, cool, square loss function, also nice. We have another one, which is called the logistic loss or binary cross-entropy. And now I know we're running out of time a little bit, so let me see how many slides we have. A lot. Okay. So let me finish this one and then we continue next week from here on, okay? So maybe we want codec. Yeah, okay, let's see what to do on the exercise. Maybe maybe not a full thing. So another loss is so-called logistic loss or binary cross-entropy loss. And for binary task, it has this sort of function. It's a simplification of some other thing, which has to do something with entropy and cross-entropy or Kyle divergence, but I don't know how much you're kind of familiar with Kyle divergence and entropy of things. So we shouldn't go there. Okay, fair enough. We don't have to go there. So in that case, you might want to remember this formula. That would be cool if you remember that. It's if you have multiple variables than just two, it's going to be a sum, and then you end up in the cross-entropy scenario for like a categorical random, discrete random variable, two discrete random variables, and their cross-entropy and the entropy of one variable. But as I said, like let's take it as a function which just works. So this function is again predicting. What is it doing? It's taking the prediction, a logarithm of the prediction, and multiplying by the true label, and then taking the, so this is basically probability, then taking the probability of the other class and multiplying by the probability of the other class by the prediction. Okay, so these are sort of probabilities, and then you can work it out to get the Kyle divergence. But you can take it as it is, as a function which gives you something like the loss. And if you think about it, so these numbers are between 0 and 1. So what is going to be the range of this logistic function? So what is the minimum of this logistic loss or cross-entropy loss? Because we have minus here, but we have logarithms. So what is it going to be? Is it going to be from minus infinity to plus infinity, or is it going to be from 0 to plus infinity? Is it going to be from 0 to something else? What do you think? I mean, you don't have to think, you just have to look in the formula and like think about the values. So everything which is coming out here are probabilities. So let's see. So logarithm of something between 0 and 1 is going to be what? How is logarithm? Yes, logarithm with base, so it doesn't matter the base, could be logarithm of base 2. I guess we're using log base 2. So the logarithm is something like that. So everything which is in between 0 and 1 is going to be something negative. Okay, cool. So here we are multiplying negative by positive, and the minus is going to be positive. Okay, cool. You follow me? Okay. Here, this is going to be again 0, 1, and this is going to be also between 0, 1. So again, we're taking a logarithm of something between 0 and 1, so it's going to be negative. Multiply by something which is going to be positive, and the negative sign here is going to be plus. Okay, cool. So we get something which is bigger than 0. That's what we want. So this is a loss. And you can also, obviously, if you do a little bit of calculus, you end up with the partial derivative, with the derivative of this loss function, right? I mean, it has one input. Sorry, two inputs, yeah. But we're interested in the derivative of the predictions, because the y is given. This is fixed. This is constant, right? What was that again? What was the y? What is this in our setup? This is the gold label. Yeah, y is the true label, and the y hat is the prediction, and we're interested in optimizing the prediction because it's coming from the sigmoid, it's coming from the model. So we want to optimize that. So that's why we care about the partial derivative with respect to y hat. So we know it. Okay, cool. So we know how to compute a logistic loss. We know how to compute its derivative. And what we're gonna do next, not today, maybe today. Yes, let me just finish here. Why not? Because then you know everything. Okay. So here, excuse me, here we had the linear mapping of inputs, and these are the parameters we want to optimize. This is just squeezing through the beautiful sigmoid function, something like that. So cool, we can do that. And now, since we know that for this example, we have this gold label, or the true label, we can compute a loss. And the loss, if this is like a square function or the logistic loss, that doesn't matter. We can do that. So now, this is the output of our graph. And what we are interested in, obviously, is to minimize this. How do we minimize this? Is that we are finding partial derivatives with all the arguments, sorry, all the parameters, W2, and so on, and also with respect to B. So this is what we need to compute in order to do the minimization. And if you remember what minimization is, it's nothing else than taking a gradient and taking the opposite step. That's what we had in lecture 2. We're gonna introduce the algorithm. It won't be anything surprising to you. But basically now we can stitch all these things together to easily compute the gradient of this loss function, because we want to minimize this loss function. So training data is nothing else than minimizing the loss function on the training data. If we reach 0, we learn the data set perfectly. Typically, we won't avoid it because maybe there's something really bad about it. We just remembered everything from training data and it won't work for new data. But as a general rule of thumb, we want to minimize the loss. How do we do it? We build it, we use the function for prediction, which is the whole thing, right? This is the function. And we have the loss, which given the GOT label and the input tells us like how off are we. And we covered it before. So we're gonna finish next lecture and maybe something on the exercises. Any questions so far? I know I'm over time, I'm sorry about it, but I guess it's important to go into detail here. So thanks a lot, I'll see you next week.